lines, medians, and altitudes. We're going to talk about all the different lines inside of triangles. Concurrent lines at the top of your notes are 3 or more lines that intersect in one point. 3 or more lines that intersect at one point. Those are called concurrent lines. Their point of intersection is called the point of concurrency, where the 3 lines intersect. Good. So I have 4 lines there, A, B, C, and D. They all intersect at one point. We'll call that point P. That would be the point of concurrency. Those are concurrent point or concurrent lines because there's more than 3 that all intersect at one point. Back in chapter 3 at the beginning of it, that's when we talked about our parallel lines. Those lines are supposed to be parallel. And then a transversal. None of these lines would be concurrent lines. I mean, I've got 3 of them, but they don't all intersect at one point. So concurrent lines all have to intersect in one point, and there has to be at least 3. Cool. Theorem 5.6, that's at the top there in the box, and it states, the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertex. Okay, so how many sides are there on a triangle? 3. So how many perpendicular bisectors will we have? 3. We'll have 3 of them. This says the bisectors of the sides. So here's one perpendicular bisector, creates a right angle, cuts that side in half. Here's the second one, right angle, cuts the right side in half. And here's the third one, right angle, cuts the third side in half. All 3 bisectors meet at one point. That would be called the point of concurrency. That point is equidistant from each vertex. The vertex, those are the corners of the triangles. So the distance from this point to the top vertex, the distance from the point to the right vertex, and the distance from the point to the left vertex are all the same. That's what theorem 5.6 says, that the distance or the perpendicular bisectors meet at one point that's equidistant to each angle, each vertex. Got it? Okay, put a little star next to that because we're going to come back to that, theorem 5.6. Theorem 5.7 says, the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides. How many angles does a triangle have? 3. So how many bisectors will it have? 3. Okay, there's 1, there's 2, and there's the third angle bisector. They all intersect at point X. This theorem says that the bisectors of the angles are concurrent at a point that's equidistant from the sides. So since these are all the angle bisectors, the distance from X to E, X to F, and X to D has to be the same. Angle bisectors meet at a point equidistant to the sides. Perpendicular bisectors meet at a point that's equidistant to the vertices. So we'll start next to 5.7.2. All right, some vocab words here. A circle is circumscribed about a polygon when the vertices of the polygon are on the circle. Circle is circumscribed about when the vertices of the polygon are on the circle. We have triangle SQR, its vertices SQ and R are on the circle. So we would say that this circle is circumscribed about the triangle. You have a bunch of segments inside of the triangle. These ones specifically that I'm highlighting are what kind of segments? Any idea? What are they doing to the sides of the triangle? Cutting them in half, so what would we call them? Good, they're a bisector. What else do they do to the side of the triangle? Yeah, they're perpendicular. They're making right angles. So those are perpendicular bisectors. The perpendicular bisectors of a triangle are concurrent at a point that is equidistant to the vertices. That's theorem 5-6. So these red lines that go to the vertices are all congruent. Okay, now look in relation to the circle. How are those red lines related to the circle? Well, I don't know. Would it be? If the distance from that point to the outside of the circle is the same as the distance from that point to the outside of the circle? Okay, so what do we call that segment that starts at the middle and goes to the outside of a circle? Starts with an R. Good, it's a radius. So this point of concurrency of the perpendicular bisectors is called the circumcenter of a triangle. Point of concurrency of the perpendicular bisectors of the triangle. Am I still in your way? When you circumscribe a circle, that means the circle goes on the outside of a polygon. The circle is circumscribed about a triangle. You can circumscribe a circle around an octagon. That just means the circle's on the outside. Where the perpendicular bisectors meet, that's called the circumcenter of the triangle. We also figured out that that is the center of the circle also. AKA, also known as the center of the circle. You know, when you don't want to use the word triangle and you put a little triangle, this is how we abbreviate the word circle. We draw a circle with a dot. That circle is being circumscribed about the triangle. It's going around the triangle. I could also say that the triangle is inscribed in the circle. It's another way to refer to the picture. Cool. Next vocab word, a median. The median of a triangle goes from the vertex to the midpoint of the opposite side. Median, from the vertex to the midpoint of the opposite side. This is our nice median. Starts at the top vertex, goes to the opposite side at its midpoint. It's cutting that side in half. From the left vertex to the opposite side, I have another median. From the right vertex to the opposite side, I have a third median. Since I have 3 vertices, I'm going to have 3 medians because they got to start at a vertex. These medians are concurrent lines. They all intersect at one point. That point of concurrency is called a centroid. Where the medians intersect is called the centroid. That's on the very bottom of your paper. Do you see it there? The centroid of a triangle is the point of concurrency of the medians. The centroid is the point of concurrency of the medians. You find it down there, Trevor, right where your thumb's at. Right. The centroid of a triangle is the point of concurrency of the medians. So point of concurrency is just a general term for a point that is where 3 or more lines intersect. If it's the 3 medians, then it's specifically called a centroid. And then there's a theorem about centroids. That's theorem 5-8 there. A centroid is going to divide a median into fractional parts, 1/3 and 2/3. You're going to always have a 1/3 chunk and a 2/3 chunk. So here my centroid C is going to cut segment GE into fractional parts, 1/3, 2/3. Most of the time you can go based off looks. Your 1/3 should be smaller. 2/3 will be bigger. If you can't, The 1/3 always goes centroid to side. The 1/3 chunk will always start at the centroid and go to the side of the triangle. The 2/3 chunk of your median will go centroid to vertex, C to E. So let's just pretend here that the length of GE, that whole median, is 15. Then how long would the 1/3 section be? Right, because thirds mean to cut it into threes, right? So 15 divided by 3, 5. How long would my 2/3 be? 10. Let's play more games. Let's say that HC is 6. Is that the 1/3 or the 2/3? 1/3. So then how long is my entire line HF? 18. This is 1/3. How many thirds does it take to get to 1? 3. So 6 times 3 is 18. What would be my 2/3 chunk? 12. Good. All right. So a centroid cuts it into 1/3 and 2/3 sections. All right. We got a little bit left until we get to apply all these. A circle is inscribed in a polygon if the sides of the polygon are tangent to the circle. This is right before or right below the theorem 5.8 box. A circle is inscribed if the sides of the polygon are tangent to the circle. You know what tangent means? Touching, yeah, in one point. Usually touch it in one point. Good. So in our picture, see how the circle's on the inside of the polygon? We say that the circle's inscribed. The circle is intersecting the triangle just at point Y right there. And just at point X right there. And it doesn't look like it down here, but tangent means it's only intersecting it at one point, point Z. The circle's inscribed. What's happening to the angles of our triangles? Triangle. Do you see the angles? What's happening to them? They're getting bisected, right? Okay, so that would mean, like, if I call this point C, TC and UC and VC are all angle bisectors. Look up at theorem 5.7. It says that the angle bisectors are concurrent at a point that is what? Equidistant from the sides. So that would mean CY, CX, and CZ are all congruent. The angle bisectors of the triangle meet at a point that's the same distance to each side of the triangle. Now take a look at the blue lines in relation to the circle. How are the blue lines related to the circle? Careful, circles have curves, so they wouldn't be able to make a right angle. It does cut it into 3 pieces. The sides of the polygon are tangent. So this blue line is going to this side of the polygon. This one point is also on the circle. It means it's touching it. So it goes from this point out to the edge. From this point out to the edge. These are the same length. From this point out to the edge of the circle, it's the same length. What do we call those blue lines? Yeah, those are the radii. So that means that C is the center of the what? Circle. In relation to the triangle, it's called the incenter, which is the point of concurrency of the angle bisectors. These are the last little words, and then we're going to apply all this stuff here. So the last vocab word is the altitude of a triangle, which is the perpendicular segment from the vertex to the opposite side. Altitude. Perpendicular segment from the vertex to the opposite side. Both medians and altitudes have to start at a vertex. When you hear the word altitude, what do you think of? What? Height, good. Talk about the altitude of a plane. How high is a plane? Altitude of Harnett Peak, how high does it go? Yeah, okay. Since altitudes start at vertices, how many altitudes will a triangle have? 3. Good. If you have an acute triangle, all the altitudes are on the inside. So on your picture there below it, altitudes are inside. All 3 of them will be located on the inside of the triangle. You have one of them drawn in there for you. From the top vertex to the opposite side makes a right angle. If I were you, you might want to draw the other ones in, because you may or may not have to do this for homework. Left vertex to the opposite side, right angle is an altitude. Right vertex to the opposite side, altitude. Notice they're not necessarily cutting the sides in half. They just have to create a right angle with the other side. Altitudes of acute triangles will always be found inside of the triangle. When you have a right triangle, the 3 altitudes, one of them is on the inside, the other 2 are the legs of the right triangle. The altitudes are the legs, and then one of them will be on the inside. If I start at this top vertex and go to the opposite side, so I create a right angle, I just stay along that leg. That's still the altitude, the height, but just so happens to be part of the triangle. The bottom left vertex to the opposite side, it stays along that leg. It's still an altitude, but it just happens to be part of the triangle. Your third one, when you start at the right angle, go to the opposite side, there's where you get your third one on the inside. Right triangles. One on the inside, the other 2 are the legs. All right, then your obtuse triangle. The 3 altitudes, one of them is on the inside, the other 2 are on the outside of the triangle. Here we go, we gotta do this so you know what to do. Number 1, find the center of the circle that circumscribes the triangle. That means the circle's on the outside of the triangle, okay? By definition, when it says it's circumscribed about, it says that the vertices of the triangle are on the circle. So each of these points, bless you, are right on the circle. We have to find a point, I don't know, like here, so that the distance from that point to each of the vertices is the same. Then that would become radii, right? So yes. Right. Okay, now flip it over so you're looking at theorem 5.6 and 5.7. Find the theorem that says some point is equidistant to the vertices. Which theorem talks about a point being equidistant to the vertices? 5.6. What's the beginning of that theorem say? The perpendicular bisectors, that's what we have to find. Go back to number 1 and write find the perpendicular bisectors of the sides of the triangle, but sorry, thought that you understood. So we have to figure out the perpendicular bisectors of the triangle, because where those perpendicular bisectors intersect is equidistant to the vertices. Let's look at the bottom side of the triangle. What kind of line is that? The bottom side of the triangle, because it goes left to right. Horizontal, right? What kind of lines are perpendicular to horizontal lines? Vertical. So we know we're going to have to draw a vertical line through that side, but it's supposed to bisect it. So it's going to pass through its what? Midpoint, louder, Ross. Good. So what's halfway between 1 and 5? 3. So we need to draw a vertical line through 3. Vertical so that it's perpendicular, and through 3 so that it bisects it. We'll just extend that sucker up. There's one perpendicular bisector. We have to find another one. Do you want to do it of the diagonal line or the vertical line? Good. What's perpendicular to vertical? Horizontal. Good. And it's supposed to bisect it. So from 1 to 7, or it's halfway between them. No. What number's between 1 and 7? Right in the middle of them. 4. Good. So there is the perpendicular bisector of that side. You only have to find 2, because where those 2 intersect, the third one's going to intersect there. This point is equidistant to the vertices. It's the same distance to each vertice on the triangle. In relation to the circle, that means that's the radii. So that's the center of my circle. What is its ordered pair? 3, 4. The red lines were representing the distance from that point of concurrency to each vertice, and they're all the same, which means they're the radii of my circle, so that's got to be the center. Okay. Number 2, city planners want to locate a fountain equidistant from the straight roads that enclose a park. Explain how they can do this. So we got this triangular park created by Andover, Mariposa, and Highway 101. We want to put a fountain so that it's equidistant to the roads. So would that look like a very good spot? Probably not. But which theorem talks about a point inside of a triangle that's equidistant to the sides? 5, 7, what's the beginning of that theorem say? So what do we have to find about the triangle then? What do we have to find? We have to figure out the point at which what things intersect. Yeah, what's the beginning of it say though? It's the point of concurrency of what segments? What kind of bisectors? Angle bisectors. The bisectors of the angles, so the angle bisectors, are concurrent at a point equidistant from the sides. So the city planners need to come in and measure the angle measure between Highway 101 and Andover. And then they're going to take a chalk line. You guys know what the chalk lines are? We pull them out and snap them. We need to go out and have some construction times. And they're going to snap this chalk line so that the angle is getting bisected. Then they're going to measure the angle between Mariposa and Andover, cut it in half, use a chalk line to figure out where that line would be so that these angles are congruent, so that they're bisecting it. And then they'll do it with Highway 101 and Mariposa just to double check their work. Where those angle bisectors intersect is where they should put their fountain. I have a nice sentence for you to fill in. Explain how. Locate the fountain at the point of concurrency of the angle bisectors. Hopefully. Number 3, M is the centroid of triangle WOR. Centroid. What did we say the centroid was? Of the what? Good. What's a median? Flip that over. What's a median?
That requires so much work.
Well, then listen better.
That requires work too. It's scooch out. I always start to see when
What's
it's
a median?
in, so I always move my bed.
A segment whose endpoints are a vertex and the midpoint of the opposite side.
Good. A median goes from the vertex to the midpoint of the opposite side. Sort of. So, where they all intersect is called the centroid. What's the theorem say about the centroid? It cuts the medium into what fractional part? 1/3 and 2/3. So if WM is 16, is that representing the 1/3 or the 2/3? 2/3. That would mean that there are 2 equal chunks here, right? What would each chunk have to be? 8. So then that would mean that MX is how long? 8. Good, because that's the 1/3. Therefore, WX would be how long? 24. Good. Because 2/3 is 8. That means, or excuse me, 16. That would mean 1/3 is 8, and then 8 plus 16 gives me 24. Neat. Number 4 is kx, a median, an altitude, neither or both. Why? Good. It's a median because it's hitting a midpoint, x. It's bisecting it, median. It's an altitude because it's perpendicular, so this one would be both. On your homework today, it's going to say explain. So your explanation would be like, it's perpendicular, therefore it's an altitude. Or it's hitting a midpoint, therefore it's a median. We're going to do like 2 more. Flip it over. We're going to skip number 5. Number 6 is my, a median, altitude, neither or both. Why? Good, because it's hitting at a midpoint. Awesome. Goes vertex to midpoint. Quick question. What would you call the segment XY? How would you refer to point X on line LM? It is LM's what? Good. What is Y on LK? What do we call a segment that connects midpoints? A mid-segment, which means XY should be what to KM? Parallel, and what else?